Okay, so let's move on to the next speaker of the day. That would be Holger Ott. And Holger is a professor and chair of reservoir engineering at the University of Leoben. Now Holger will present to us a talk titled Numerical Interpretation of SCAL Experiments Using MRST. So Holger, the screen is yours. Please go ahead.
Yeah, thanks a lot. Try to share here. Can you see the screen now?
So currently we only see your camera.
You see just my camera. Okay. Okay. I have to push once more the button.
There we go.
Perfect.
Very good.
Here we go. Okay. Perfect. Now you see it. Perfect. Yeah. Good afternoon, ladies and gentlemen. Before I start with the presentation, I would of course like to thank the organizers for inviting me. Even so, we are not heavy MRST users. Yeah, I would say we are rather newcomers in this field. So far, we use MRST for our reservoir simulation teaching classes. We combine MRST with commercial simulators like Eclipse, Petrel, and so on, in order to give people the hands-on experience, developing something themselves, but also learning to deal with the commercial tools they likely will use in their professional life. Okay, and by the way, I'm an experimentalist, so this means, well, if there are questions about hardcore MRST and interpretation, then I have my colleague Omideza with me, a PhD student in my chair, and he has a poster presentation, PSO3, uncertainty analysis of SCAL data, which refers exactly to the simulation tool that I would like to talk now about. So also the SCAL interpretation tool. Let me switch the slide. How does this work? So the SCAL interpretation tool was also initially developed for teaching purposes. We have here as well a SCAL course where people learn the experimental techniques and the interpretation of this data. But in the meantime, we are doing all kind of data analysis with it, and it works really good. So I think you have all a reservoir engineering background, or most of you, but for those who are not familiar with SCAL, SCAL stands for Special Core Analysis. And let's say, in contrast to routine core analysis, which deals with rock properties, porosity, permeability, and so on, SCAL deals with rock fluid interactions. So this means with multi-phase flow parameters, and predominantly on the forefront, there is of course relative permeability, capillary pressure that determines in the case of 2- and 3-phase flow, of course, whatever the reservoir performance. So these are for us very important parameters. And just to give you an impression on what SCAL means, a SCAL program is typically very time intensive and also very expensive. Time intensive means, well, a SCAL program may take several months, half a year, maybe even longer. It depends how extensive it is, of course. And respectively expensive it is. And also there is always a lack of bugs that can be investigated and so on. So it's a tricky business and a lengthy business. And the problem is that if you give your data, or not your data, your course to companies, to SCAL laboratories, then typically they use analytical models for evaluating their data. And this is completely insufficient. So a little bit more advanced laboratories or companies, they use, of course, numerical interpretation of SCAL data, but this is not yet really common. Yeah, so there are individual labs doing this. It's rare, and this kind of SCAL simulators are typically proprietary or they are commercial, one of both, right? So you cannot easily access them. And this was the starting point, coming myself from Shell, also from the SCAL team, to develop our own simulation tool. So good, but before we go into simulation, I first have to brief you a little bit on the experiment. Yeah, so this is half experimental, half numerical, my presentation. And I picked out the most simple, conceptually, not from the experimental procedure, but conceptually the most simple experimental method. And this is the steady state relative permeability measurement. So what are we doing here? We have a plug, so typically standard plugs 1 inch diameter and 5 centimeters long, for example, right? We inject oil and water simultaneously. So this means we establish a certain fractional flow. And by covering different fractional flow points across the fractional flow curve, we can cover the whole accessible saturation range in this kind of experiments. So this means we change then the relative flow of oil and water by keeping the total flow constant typically. So what we get and information is of course a differential pressure. So you see here a typical steady state experiment, it goes up and down like a pyramid. And in the middle, of course, we have the highest differential pressure because there the relative permeabilities are crossing each other. And this leads then, of course, to the largest resistance to flow. In addition, of course, we need to have the material balance. Sometimes people get this just from sampling and from looking what comes out, additional production, so to say. But typically what is used is X-ray source and a detector. And with this, we can get saturation profiles like you see here for different fractional flow steps. Yeah. So if we have that, then we can, and as analytical solution, make our life very simple. So we can, for example, use simply Darcy's law. We know all the other parameters, and from the delta P, we can calculate the relative permeability of water and oil. Very simple. And of course, independently from the saturation profiles, we get an average saturation that can be associated, assigned to the relative permeability. And with this, of course, we get a relative permeability curve. Yeah, with which we can work. This is not too bad. It's common standard in oil and gas industry, so to say, right? This is what people are doing. So now this is what we call a friendly data set, yeah, because here you see that indeed the saturation profile has no capillary end effect and it's rather flat, and you can say, well, an average saturation makes somehow sense, but what if we have a different situation? For example, here we have a data set about which I will discuss a little bit later in detail. And you see here strong capillary end effect. This has to do simply with the symmetry break from in the core and outside the core. This means going to PC is equal to 0 in the outside of the core. So you see here the capillary end effect. This means now for one line corresponding to one fractional flow, to one experimental step, we see that there is a range of water saturations. Yeah, so this means I cannot simply assign to one plateau, one water saturation. That's not possible. So this tells us first that capillarity is present in relative permeability measurements. So this is crystal clear. So we would have to analyze this somehow in a combined way. And there is a non-unique SW for individual FWs. So basically what we need is, of course, at the end, we know this numerical simulation for that, and we need to simulate simultaneously and, the information that we have to extract KR and PC at the same time. Good. So this means just a little brief summary in between. We have analytical solutions. They are insufficient, as I mentioned. They are based on assumptions. Assumptions are, for example, that KR and PC are not coupled, but they are in the experiments. For example, if we think about not a steady state, but a Hassler-Brunner and centrifuge experiments, then, for example, there the invading phase viscosity is neglected. Yeah, so this means there are very wild assumptions that narrow down basically the applicability of this kind of analytical methods that are used frequently. So this means what we want to have simultaneous numerical data interpretation, including the full physics. And additional benefits is that we get, if we do it in the right way, uncertainty ranges that we can play with the data, so to say. And this is, of course, really of importance for us for QA/QC. Basically, SCAL is always about quality, and we get uncertainty ranges. With the uncertainty ranges, input for stochastic reservoir modeling. And all modern reservoir modeling goes into not just one representation, but into a stochastic type of approach. Good. So, but now the implementation in MRST is as simple as you can think of. Yeah. So this means here on this presentation there are more type of experiments, but in this presentation we use steady state data and centrifuge data, and we developed two domains, two simulation domains, very simple, one-dimensional, equidistant gridding. So this is for a lot of people like you, it's maybe boring. Yeah, so the domain itself. And what we are solving is, of course, typically, well, in this case, immiscible incompressible flow. Also, this is not very sophisticated, but it's absolutely what we need here. And we solve the material balance, the momentum balance. And for the centrifuge, we spin the sample around the center of rotation, an axis of rotation. And here we need to introduce the body force that is displacing or driving out the fluid, so to say, by gravity and by a varying gravity, because it depends, of course, on the distance from the axis of rotation. Therefore, the gravity is very high and is varying across the domain according to the distance from the center of rotation. Good. So the first thing that you would do, and this is a trivial step, but it's absolutely needed, is to benchmark your simulator. Yeah, so we use the synthetic data set as published earlier by Leoben et al. And basically in this paper, they compared different simulators, like famous simulators like Siroos, Centra, or commercial simulators, so to say. Right, and of course we just take the data set and we benchmark our simulator against the data set. So these are the input parameters. So we have a primary drainage and an imbibition, relative permeability, and the same for the capillary pressure. And what we are matching is simply all data that they provide. I show you here steady state. So the Siroos simulator, for example, is now the dots, and the line is our simulator. An unsteady state, so that's a normal displacement experiment, so to say, and here the centrifuge data in primary drainage. So this means we are matching them, and as you see, and we expected that, of course, everything is all right, you get a perfect match, and this doesn't tell us more, but also not less than everything is implemented nicely. So this means tick mark. Yeah, so that's important to know that it works. Okay, and with this now, with the simulator, we go now into a workflow, and this is our simulation strategy that I have here. It starts, of course, we are talking about interpretation of experiments. It starts with the experiment. So that's the truth, so to say, right? The experiment, and here, especially we talk about steady state and centrifuge, as I told you. Well, in the next step, of course, we use the analytical solutions. In this case of steady state and centrifuge, that's the Darcy equation and the Haslett-Brunner equations without explaining them in detail. We go into the data set and we derive a first estimate of the data here just for the relative permeability from the steady state. In the next step, or this gives us already, let's say, a kind of initial guess, a starting point for the simulation. But in the next step, we have to define what kind of representation do we want. Yeah, so there are different representations of capillary pressure curves and relative permeability. For REL-perms, that's a little bit more known or better known is, for example, Brooks-Corey, LET, and whatever. There is also other type of representations. Whatever. And basically, these are power laws. And here I have also point by point. I will mention this a little bit later. But with this, we compare now let's say the experimental data or the analytical solutions to these representations, and then we decide what we are doing and which one we are going, so to say. This means we have a good starting point for the numerical simulation, having chosen a parameterization. So this is the starting point that we need. And then the numerical simulation start, so to say. This means we go into, familiar to all reservoir engineers, we go to a classical history matching. Yeah, for this, we have to choose an objective function. So here is our choice. And this, so far until this point here, we have implemented this until the forward simulation into MRST. But then we have to go into MATLAB, and we use for this kind of thing the MATLAB optimization toolbox. Yeah, so this means we have to minimize our objective function to find the best match to our experimental data. Classical history matching, we get exactly one representation, the best match at the end, but this is of course not enough because we are interested in stochastic reservoir modeling. Therefore, we need to make statements about the uncertainty. How to do that in the next step? We use Monte Carlo Markov chain Monte Carlo sampling method to sample our solution landscape at the end. Yeah, we use the likelihood estimation function with constant errors. These constant errors refer now to our experimental errors that we have to assume out of our data sets, like fluctuations, whatever reading uncertainties and this kind of things, right? And on this we make a Markov chain Monte Carlo sampling. So the result of this, here's the library that we are using, the Paramonde library. And the result of this you can see here just schematically. So what we get is, if we have different parameters from our parameterization, this means coming from, for example, this Corey representation, this power law, we can now get the histograms. So this means the single parameter probability distributions. We can also get the 2 parameter probability distributions, right, or projections here. And you see that there is already, between this arbitrary parameters, there is already a trend. Yeah? So you see that there is a trend between parameter 1 and parameter 2, and this trend can of course be expressed by a correlation strength. And this correlation strength, in this case, it's of course negative. The slope is negative, and it's a moderate correlation, so to say, right? But this helps us basically to understand how our parameters combine, let's say how they depend on each other, and B, from the histograms we can also get basically by applying, for example, P10 to P90, let's say thresholds, we can define an uncertainty range for our data that you see here in red and in blue. Yeah, and this is exactly what we need if this is really a fair type of error, then this is what we need as input for the stochastic reservoir modeling. And as input for databases, where I typically work with this kind of correlations of different properties. Good, so this is the workflow that we are using. So this means our domain is very simple. Yeah, so one-dimensional homogeneous. This is what we need for SCAL. This is not because we are lazy, but this is rather because of the nature of SCAL. This means the data we want to get out, the relative permeability that we want to get out, the capillary pressure, should be representative for the rock type, and therefore we have to assume this as homogeneous, and typically this simulations are done in 1 dimensions. And then we apply this workflow. Okay, good. So let's test it. The same thing. We use a synthetic data set. Yeah, the data set is now by Leoben et al. You see here 3 different relative permeability curves. You see very generic, of course. Yeah. So this one here, the black one is the initial starting point. The red one is the truth. This means the input for this synthetic data set. And in blue, you see our match to this, which is quite good. Okay, here the data are truncated. Here you may run a little bit in problems, but otherwise the match is perfect. Also for the capillary pressure curve that you can see here. Here, basically, in contrast to the relative permeability, you need to introduce upper and lower boundaries for the simulation. Okay, good. So this is the input. We go through the process. This is the result. What you see, the parameterization that we are using here is Brooks-Corey for KR and Skeveland for PC. And here you see the results. As I say, the histograms and the 2 parameter correlations. You can get information out of this contour plots, so to say, and you see that some of these correlations are stronger and some parameters do not show any correlation, which is then again reflected in this kind of correlation strength matrix as explained before. And what we learned from this correlation strength matrix is somehow maybe clear. Yeah, for example, relative permeability, endpoint relative permeability at Connaught water saturation must depend on the Connaught water saturation, right? It's a strong correlation. And so we can learn a little bit about the correlations in our data, so to say. In this case, it gives us more information about the parameterization itself because it's a generic model. But if we go to real data, then we can learn about the displacement physics. Good. So now, I'm quite late already. Okay, let's go through This is now an example, Esteliades limestone, where the world is not that simple like with the synthetic data sets, right? It's a complex carbonate. You see here macro and micro porosity embedded, so to say. This is a steady state experiments. You see here this capillary end effect. And here are the analytical solutions out of 2 steady state experiments. We have in addition 3 centrifuge experiments and several porous plates. So that's an extensive data set. Therefore, we are going to that. So we are using this relatively old data to reanalyze. Okay, what happens if we apply the analytical solutions? Well, this happens. Basically, we see there's a perfect fit or not a good fit, a little bit too high maybe. For the centrifuge data, the average water saturation here, we see the fit is not very good, but it's also not completely unacceptable, I would say, right? So here, for example, here we use PCs equal to 0 because the analytical solution is made for that. But what if we combine both? We now model, forward model is our forward models. Yeah, we forward model including KR and PC, and what we see, it doesn't fit at all. Yeah, so this means the combined information doesn't give us a match. So it can just be the initial point, what I mentioned before. Okay, good. Then the next step would be the assisted simultaneous history matching of 2 data sets. Yeah, we have here again centrifuge average saturation, delta P and SW profiles for the steady state, and this is the centrifuge. Yeah, let's do that. Basically, simultaneous fitting with using a Brooks-Corian and Brooks-Corian equivalent parameterization. Well, doesn't work. Okay, bad luck. So this means especially here, basically in the middle of the saturation range, yeah, and then there we have a huge mismatch basically, and here the capillary end effect we also do not get. Yeah, so that's the best combined fit, the best combined match for, and it looks the same for different parameterizations. Also LET, which is more flexible, delivers us a similar result. Yeah, so this means parameterizations do not work in this specific case, maybe for sandstone, for this one not, yeah. So what about point by point? So point by point match you see here below, yeah, perfect match, more or less. If you have seen matches of relative permeability and capillary pressure data, then you appreciate that this is a perfect match for point by point method. Of course, it's clear that we match it, yeah. So we go from 12 numbers of the number of parameters from 12 to 45. Of course, the more freedom you have, the better you can match, of course, complex shapes. No question, but we also do not need a lot. Yeah, we just need to constrain the curve somehow that they have a monotonic behavior. Yeah, if the water saturation is decreasing or increasing, then of course the water mobility should not decrease. Yeah, so this means there is a reasoning behind the monotonicity. And we get here perfect fit. Good, just at the end, going into the data that we obtain with that. So you see this is not clearly following a power law. You see here as well what we assume from the data, that we have a very low mobility at a crossing point. And what we observed is that the analytical solution is not so far away from the perfect solution, yeah, from the sophisticated solution here on a logarithmic scale. This is now our P10 to P90 based interval for now here for different assumed errors, experimental errors. Yeah, so you see here 3% of water saturation error and here 1%. 1% is a bit low, 3% rather realistic. And so you can play around with the data and you can say a little bit about what your data mean and what is an honest evaluation of this kind of data for stochastic modeling. Well, you can see this is of course P10 to P90 come of course from the histograms. You can see here the histograms here very broad, also non-symmetric, so to say, and the lower the water saturation becomes, it becomes more symmetric. So this may be a result of our not sufficient sampling rate at the end. Here you can also project then the error range, so to say, on your raw data, so to say. And now basically we come to the strengths and weaknesses of this kind of procedure. So the strength is clear. So we get a perfect match. And I think it makes absolutely sense also in comparison with the analytical data. And the weaknesses is also very clear. So if we look to the correlation strength matrix, well, we see something, but it's very difficult to interpret. So we have a slight idea what it means. So to say, the coupling of PC and KR should be visible here, but we are still in the course to understand this a little bit better. So this correlation strength matrix is not anymore a very clear matrix. And at the end, due to this fact that we don't deal with physical parameters like residual saturations, powers of a power law, for example, right, exponents of a power law, it's difficult to build correlations basically in a correlation database. Well, good. Here we have a little bit about sample-to-sample variation. I'm skipping this in view of time, but just very briefly, what you see is that if you combine one steady state with different capillary pressure curves, then basically you see that whatever the results are laying on each other, more or less, right? But if you go from one steady state experiment to another one in an outcrop carbonate, basically, as homogeneous as you can get, then you see that the sample-to-sample variation is outside the P10 to P90 range of the individual data set. Yeah, and this means basically at the end that our sample volume is not really representative. That's a common problem in carbonate rock interpretation, so to say, right? And we are working in the moment, and with this I come to the summary and outlook. We are working in the moment on this issue. We have, for the same rock type, the same fluids, we have larger scale experiments and steady state experiments, and we try now to do an upscaling from this data with sample-to-sample variation with the intrinsic uncertainty, so to say, projecting on our unsteady state experiments to understand better how to come up with a good description of the rock type, so to say. So this means summary. We have here a non-proprietary, non-commercial SCAL data interpretation tool. So we also would like to share this with the community. Different representations for complex saturation functions. So this is something completely new. Uncertainty modeling for robust input for stochastic reservoir modeling. What we are doing, we work in the moment on the graphical user interface a little bit and on optimizing everything so that it maybe also runs a little bit faster. And what I said, investigation of sample-to-sample variation in terms of upscaling, and we try to combine this in the moment as well with digital rock analysis. This means calculating from even smaller size samples, so to say, to make an upscaling, a downscaling step to later upscale digital rock data. So this is what we are doing. And with this, too late. Sorry for that. Took always talking too much, but I would acknowledge, of course, my co-workers. In the first place, of course, Omideza, who developed this. So this means questions about implementation go to him in the poster session. Siroos and Pitt also helped a lot for this project, and I also would like to acknowledge helpful discussions initially of US Mass. And also discussions with Stefan Bergs are highly welcome. Yeah, thanks a lot. And I just managed a half an hour, I guess. Yeah, sorry for leaving not too much time.
Thank you very much, Holger. Very interesting presentation. And I think it's really nice to get an experimentalist's view on how you can make use of MRST as well. I think we have time for, there's 2 minutes left, so let's take a few questions. There's multiple in Zulip. I hope you can find some time to monitor that chat and answer during the symposium and hopefully also afterwards as well. But we'll take a few now. The first one is from Daniel Wang. What prior distribution do you use in the Markov chain Monte Carlo portion of the workflow?
What? Say it once more, please.
So his question is, what prior distribution do you use in the Markov chain Monte Carlo portion of the workflow? I guess you used the optimization toolbox in.
So toolbox, yeah, the optimization toolbox. Yes.
Yeah, and yeah. So the question was regarding what distribution, if you know.
Yeah, it's very likely goes also to Omid, but very likely a Gaussian distribution initially.
Okay, thank you very much. And then let's take one more. This is from Nikolai Andrianov. Do you use a derivative-based optimization in minimizing the objective function? If yes, how do you compute the derivatives? if you're using a kind of downhill simplex, aka a MOBA method, how do you account for the constraints?
So thank you for this question. Yeah, it is gradient based. Yeah, so this is what I can tell you. But the exact implementation, I would as well refer here to Omideza, who can tell you this very likely in detail. But it's gradient based. Very good. Yeah, so as you say, there will be a poster. I think that's PSO3 in the poster session later. So if you think this was interesting, please do check that out, and you can probably get more answers there as well. And also use Zulip to ask questions both now and throughout the symposium. Thank you very much again, Holger, for a very interesting presentation.